If we have a force field, let's say, and we have a short segment of a path through the force field. For example, let's say that we move along a path like so. So we move a short displacement. So let's call this a displacement vector. We'll call that a delta S, a displacement. Now, if we have this displacement and a force acting in another direction, well, let's look at a bigger picture of that. Let's suppose that our displacement is here, and our force, taking some liberties with the scale of our picture, let's say that our force is like so. Now, the way I've drawn the delta S and the force here, the force would be much bigger, the delta S much smaller. But let's say now that we just have some force and some displacement. If this force remains constant over this displacement, then it does work corresponding to this displacement, and the amount of work done by the force is just the component of the force perpendicular to the displacement multiplied by the distance, so that we have some parallel component of the force acting in the direction of our motion, and that parallel component is nothing but the projection of the force onto our delta S vector. So that we have this projection, we have this delta S vector, and the work done on this interval that I'll refer to as delta W equals that projection times delta S. Now, it's a little clumsy writing out projection delta S of F. It's not a very compact notation, so I'm going to simply call this projection F parallel, the force parallel to the displacement, so that the delta W is the magnitude, well, it's F parallel times delta S in a sense. And the sense in which that's so is, if F is in the same direction as delta S, then this work will be positive. If F is in the opposite direction, then the work is negative. Now, if you know a little bit of physics, you understand what we're talking about. Otherwise, just accept this definition. This product, it looks like the product of two magnitudes. I haven't finished writing it. I'm going to put vectors over these, and I'm going to put a dot in front of them. So this is now a dot product. You know that the dot product is positive if the two vectors are in the same direction, negative if they're in the opposite direction. F parallel is in the same direction as S, as delta S, so that the cosine of the angle between them is either 0 or 180 degrees, either plus 1 or negative 1. Now, if you think about it, then this is just going to be the magnitude of the projection times delta S, positive if the force component in the direction of S is in the same direction, and negative if it's in opposite direction. Without going into all the details, you can verify this. This is nothing but F dot delta S. We didn't really have to come down to the F parallel and the projection and everything. However, having done so gives us a better picture of what we mean by the work in the F dot delta S. In terms of the angle between the vector, between F and delta S, of course, this is nothing but the magnitude of F times the magnitude of delta S times the cosine of the angle between delta S and F. Now, if this delta S is part of some path through the force field, let's just say we're moving in and out, and we're moving along the path, and we come down here, and this represents part of the path, or at least approximates part of the path. Let's just say we got a path that starts here and moves all the way around this curve and comes back to its original point. We want to see how much work it requires for us to move around this path. Now, if we want to actually calculate the work, we're going to have a formula for our force field, and we're going to have some parameterization of the curve. But if we have an expression given a function f and maybe a parameterization of the curve, we can find or at least we can try to calculate the total F parallel delta S over the entire curve. Our strategy for doing that is going to be to partition the parameterization or the curve. We're going to partition the range of the parameter, but let's not get into the details. Just conceptually, we're going to partition our curve into small pieces. For each piece, the direction is not going to change very much, and we're going to have some length, maybe a fixed length along the curve, maybe a fixed interval of our parameter, with sample points, etc. In other words, we're going to get something that leads us to an integral, and find the expression for the sum of F parallel, let's say sub I, times our delta S sub I, or a sum of F sub I delta S sub I. Now this is vague. I'm just writing this notation to remind you of what you know about the process of integration. We'll make all this specific. We haven't even said what our variable is for the function. Of course, that'll probably be f will probably be a function of a point in space or the point in the plane, and the parameterization will give us points in space or points in the plane. We'll worry about the details of this later. Right now, we just want to think in terms of the concept of a function, a vector field, and a curve, and how we could calculate, say, work around that curve. And we would do that by a process of partitioning and using sample points, evaluating the function at the sample points, evaluating our delta S for the intervals of our parameterization, and so forth. Having worked through the details of this partitioning process, we will end up then taking a limit and what we end up with is an integral of f dot ds. over some range of the parameter, etc. And this is going to be what we call a line integral. It's an integral of a quantity, in this case, contribution to the work, over some curve. And different line integrals can have different meanings, but this represents kind of a typical meaning. So what we've seen here is that we have this process for calculating, let's say, the work as we move through a force field, and this process leads us to something we call the line integral. Let's make a little correction here. A function, it's a function, and just put a note up here that summing up work done along a path leads us to the idea of a line integral. In general, a line integral sums some quantity along a path, along a curve, or what we've referred to here as a path.